In this chapter, we're looking at estimation, and the importance of estimation is that what we're essentially building on here is our ability to talk about how valid and meaningful a sample is in talking about the population as a whole. So most of the time what we're doing here is, instead of talking about the true mean or the true standard deviation, what we're talking about is point estimation. Alternatively, if we don't want to estimate the point, we can get the probability that we will choose an interval or a range that the mean is likely to exist in, and build from that a confidence interval. So let's talk about what we're going to talk about here. So we're going to start here by talking about the interval estimate of the population mean. And what that's going to do is, again, talk about how we can talk about a population when we might not have all the information about it. And what's going to be introduced to you here for the first time is the T distribution, and we'll look at how that's a little bit different than the normal distribution for a set of statistics. So essentially what we're doing in this topic is, we want to be able to talk about the mean of a population when it's just too impractical or just impossible to know, to get that census. And so, again, what we're trying to do here is be confident that when we take a sample and we calculate the mean of that sample, that it might be meaningful estimate or approximation of the mean of the census as a whole. Okay, so again, the reason why this topic is called estimation, and what estimation precisely is it means that not using the census, not using the population as a whole, that when we have a sample and we calculate the mean of that sample, how meaningful is it in estimating the mean for the census? There's obviously going to be typically a margin of error when we're talking about going from a sample to a census. So we're going to build up that margin of error estimate, as you see here, and then we're going to build a confidence interval. How confident are we with a, for instance, 95% confidence level that the mean that we're stating from the sample is what the sample is for the population as a whole? So, let's say that we have a large, let's say that we have a large sample, and since this is a n that's greater than 30, then what we know is that, generally speaking, what we can say is that we can set up two situations, one where the standard deviation is known and one where it's not. To build that confidence interval, what we would say is that the mean, the population mean, is going to be plus or minus the standard deviation, when it is known, divided by the sample size, versus when we don't know what it is, and when we don't know what it is, then again, we're going to build up that confidence interval. What you can see here is that what we're trying to do here is, we're taking, we're dividing up our alphas here for our tails, our left tail and our right tail, and we're focusing on that 1 minus alpha, our confidence interval. So if I want to talk about having 95% confidence interval, this 95% here, the remaining 5% is going to be equally divided between these two tails. So 2.5%, 2.5%, 95%. So we would be trying to calculate that confidence interval there, dividing each of the tails out. And that's what you see on the next slide here, what I just said. Let's build this out here. So let's say that we want to find the 90% confidence interval and the 99% confidence interval. Well, let's start with 90 here. So if we're looking at the 90% confidence interval, then essentially we need to put 5% in each of the tails. So we're going to be finding a total area of 10% with it being divided on either side, the 5%. So now we need to look at the standard normal table, and we're going to try to find it for Z05 on the right side and the left side. So let's do that. So Z at 0.5 Z at 0.5 and negative 0.5. So what we're going to look at here is the 0.95 let's see here, 0.95 sorry, I need to do it on the other side. Sorry, I'm trying to find the right table here. I know I'm in the right area here. Let's try to find our thing here. So I'm looking at 0.95. And you can see right here, it's about 0.82. Sorry, no. I think I got it good enough here. Okay, so if I'm looking for, I need to look for, where would I find 95th percentile? So I'm looking for, let's write it out here. Okay, so let's try to see how close we can get here. So we're looking for 0.95. What do we see here? Looks to be about right here. Okay, so I know that if I want to find something where it's approximately 0.95, it's got to be with a z-statistic of about 1.64 or 1.65. And based on that, I guess you kind of see that right here, we can take the average of that to find this. So that gets us that 1.645 is the average of 1.64 and 1.65. And based on that, right, so that, we should say here, that gives us an idea of what types of z-values we would have to have that 90% confidence level. To go to the 99% confidence level, that would be 0.5% on each side. And so now we'd be looking for 0.9950. 0.9950, right about right there. So it should be about 2.57 and 2.58 would be where we approximately at 0.9950. So that, again, that would give us an idea of what kind of z-statistic we would need to see is about, in this case now, about 2.575. Oh, yeah. And we see that right here. So essentially what we're doing here is we're looking for those statistics and trying to find the z-values that gets us that, that gives us that confidence interval. Now, when we take this a little bit further here and we want to start to build up a normal distribution, the normal distribution at least is set up a lot like the normal distribution. At least its structure is somewhat the same. It still has a bell shape. The only difference, as we kind of see here, is that there's two things. First, the T statistic or our T distribution, it's a little bit, the tails are a little bit higher, I guess, or as the text says here, heavier. But basically what you can see is that if our red line here is our normal distribution, the values are a little bit higher when we're talking about T distribution. But also what becomes important here is that each T distribution has to have, we have to look at our degrees of freedom, which is going to be different than a normal distribution where we don't look at degrees of freedom. Now, what that means for us here is that we can, if we have a T distribution that, so starting off first with, if we have a population that's normally distributed, but the sample size is a little bit small, then we're going to build up, again, a confidence interval based on whether the standard deviation is known or not. And then what we're going to do is we're going to look at our degrees of freedom, and that's going to tell us, that's going to allow us to calculate what our range is going to be, what our interval is going to be for each of the sides of this. So let's look at this example here to kind of make sense of this a little bit. So again, we're using our T distribution when our sample size is a little bit smaller here. So here we have a sample size of only 15 that's drawn from a normally distributed population. Here we have a known standard deviation, sample standard deviation of 14, sample mean of 35. we want to construct a 95% confidence interval for the population mean. Okay, so let's look at how we would solve that. Then, if we know that we want a 95% confidence interval, we know that we're going to have 2.5% on each side, on the left tail and on the right tail. We have a sample size of 15. That would give us 14 degrees of freedom. That's n minus 1 is our degrees of freedom. So 15 minus 1 gives us 14 degrees of freedom. And now instead of a z statistic, we're calculating a t statistic. So we need to calculate the t statistic at 0.025. So let's go here. So we have 14 degrees of freedom right here. And we are looking for the 0.025, so that's right over here. So let's go down here. And so what we see here is that we have a 0.025, that we have a value here of 2.145 of our t statistic at the 2.5% for each of the tails for 14 degrees of freedom, 2.145. Okay, so that's how we used our t statistic table. Going back to the slides here, what we see then is what we're is taking our sample mean of 35 plus or minus the t statistic value of 2.145 times our sample standard deviation over our sample size. And so what we see here, right, just going back here, our sample standard deviation of 14 over our sample size of 15. So that helps us then build what that confidence level is. That it's the sample mean of 35 plus or minus 7.8. So what we know is that, as this last statement says here, going through all that work, what it tells us is that we have a 95% confidence that the population mean, which we don't know, that the population mean is going to lie 7.8 plus is going to be 7.8 is going to deviate 7.8 from the sample mean of 35. So that would mean you need to calculate both sides. So you could do 35 minus 7.8, and you could see that the low end of that 95% confidence interval is 27.2. And then you could add the 7.8 so that you could see that 42.8 would be the upper end of that 95% confidence level for the population mean. So that's pretty useful for us to know, because again, sometimes the population is completely unknown. And now we can say with some confidence, although this is a pretty wide interval, but from a sample size of only 15, it's some pretty valuable information we got from a sample size of only 15. Now what happens when the sample size is a bit larger? So let's say we have a larger sample. Then our confidence interval to go from sample to population, that equation is now different. Okay, so with that said, as long as our conditions are held for us having a large sample, which would be n times p hat being greater than or equal to 5, and then q hat being greater than or equal to 5, we can follow this equation here, which, let's look at an example here. Let's say that we've got a let's say that we've got a proportion of students who are going to a large college who are female, and that we take a sample of 120 students from that college, and that there are 69 of those students are female students from that sample. Now, what we want to do is we want to construct a 90% confidence interval for all the students, for the census. So basically, what I've done here, let's try to reword this here a little bit more clearly. I have there's a huge population of students at the college. I pick out at random 120 students. Of those 120 students I just picked out at random, 69 of those students are female. So what would that be? This is a simple calculation here. About 57.5% are female. So I want to build a 95% or 90% confidence interval that the population is also 57.5%. Like, what would that range have to be where it'd be 90% confident that the population mean is around 57.5%? What would that range need to be around 57.5? Let's build it up. Okay, well, I've already calculated it, but 69 divided by 120, that's our population, that's our proportion, 57.5%. So, if I want to build a 90% confidence interval, that would mean I'm going to have 5% on each tail. And I need to look at my standard normal table. Okay. So if we're looking here for z at 0.05, Okay, so it's about, sorry, not this one. That's about, it's good enough here. So it looks like it's going to be between 0.05. So about right there, right? Because I'm looking for 0.95. And so it looks to be between a z statistic of about 1.64 and about 1.65. Take the average of those, that would be 1.645. Hopefully that's what we're going to see here. Yep, that's what we see here. So we then take our proportion, 0.575, plus or minus our z-score of 1.645 times the square root of the 0.575, parentheses 1 minus 0.575 over n, which is 120. Plug and chug, my friends. Plug and chug. Put that into your calculator, and we'll see that the 90% confidence interval would be our 0.575, which comes from our proportion, plus or minus 0.074. So then subtract that, add that to this, and you'll see that the range is 0.501 to 0.649. See how useful that is? Like, we've got a 120 students, a population that we don't know exactly, but now I can tell you with 90% confidence what that population mean would be. See, now we're actually getting to some statistics that's useful here that I can take, and what the statistics do. It allows us to talk with some level of confidence and sophistication about how to go from a sample to a population. And that's what I can do here now. 120 students that I know a great deal about. I know how many are female and how many are not. And now I can speak with some confidence about what that the population of the college is. That with 90% confidence, I can say my campus is overwhelmingly female. At least a simple majority is female. Okay, so the question then becomes, how big is too big? Or how big is big enough, I guess would be another way to say it. What would be the minimum sample size I would need to calculate various confidence levels? Well, we have a statistic for it. I need to solve for n. So, right, this would be before you said that you were going to calculate, that you were going to survey 120 students. We could actually calculate so that I could tell you how many students you needed to survey to be able to speak with any confidence about what the population statistics were. So let's give an example here. How many would I have to sample? How big of a sample size would I need to be able to construct a 99% confidence interval for a mean of the population with a margin of error of 0.2, with the population standard deviation being 1.3. All these numbers, we're going to plug them into our equation here. See, aren't these the times when you're glad this is an online class and you don't have to remember this statistic? So we want a 99% confidence level. And so that would mean we'd have 0.5% on either tail, right and left. We now need to go to our standard normal table for 0.005. That's going to be about right here. Right, I can find 0.005. So that is what? Between 2.57 and 2.58. So that would mean 2.575, right? The difference between the two. Oh, thank God. And so then what are we going to do here? We're going to take our 2.575 and we're going to square it times our standard deviation squared, that's our 1.3 squared, over our error factor of margin of error of 0.2, and we're going to square that. We're told to round up in general. So we could see that we would need a sample size. Again, this is a very meaningful number. We're actually now at a point in this class where the numbers actually mean something pretty cool. That we need the sample size of at least 281 to be able to speak with 99% confidence about what the population mean is going to be when the error term is 0.2 and our standard deviation is 1.3. So now you could make money consulting for a firm to tell them what kind of sample size is sufficient to be able to speak with any confidence. Alternatively, we can start to build up what we, what we need to do if the proportion is unknown. And when it's unknown, we're just going to use our proportion at 0.5 when we don't know what our proportion is. So if we want to build up what the estimated minimum sample size is going to be within a certain confidence level and build up a confidence without knowing what the proportion is going to be, let's look at this example of how to do something like this. So we've got a dermatologist who wants to know how many people put on sunscreen before they go out. And so if I want to be able to know what that answer is with 90% confidence within 3 percentage points, how big of a sample size do I need? Okay, so 90% confidence, that means I'm going to have 5% on each tail, 3%, 3 percentage point error term, so E is going to be 0.03. We need to find, again, our from the standard normal table where we're going to be about 0.05. Hopefully this should be becoming a little bit expected here. It's between where we are at 1.64 and 1.65, so right here is where we'd get our 95%. We see that here. But again, since we don't know what the proportion is, we're going to put in 0.5. Solve it. Now we see, now notice what happens here now. The sample size has to grow considerably when we have less information, in this case, about what the proportion is. So now we need a sample size of 752. Okay. Again, much of the content in this chapter, this is just an incredibly useful chapter just for life in general. But again, a lot of these things are going to make a lot more sense as we look at the homework questions, which again, I'll create videos for to kind of walk you through how to solve those things.